Bona tarda. Good evening. Secretària General de la Universitat de Lleida, vicerectors, degans, directors de centre, doctor Savageau's family, digníssimes autoritats, senyores i senyors, benvinguts i benvingudes a l'acte d'investidura del professor Savageau com a doctor Honoris Causa per la Universitat de Lleida. I welcome to the investment ceremony of Professor Savageau as Doctor Honoris Causa of Lleida University. És un reconeixement de la seva trajectòria professional i humana, alhora que posem de manifest el compromís de la nostra universitat amb la recerca i la docència, ja que a l'honorar la seva trajectòria universitària ens obliguem a tenir en consideració el seu exemple. Tot això fa que la universitat reservi per aquest acte un ritual solemne, de sabor antic i d'un tal valor simbòlic, virtuts que en aquest marc històric tenen un notable valor i significat, ja que, com vostès saben, aquesta església de Sant Martí era la seu dels actes més solemnes de l'Estudi General de Lleida i és l'únic vestigi que resta en peu d'aquella venerable institució universitària. Gràcies al conveni recentment signat amb el Bisbat de Lleida i el Consorci del Museu de Lleida Diocesà i Comarcal, la nostra universitat recupera avui la que havia estat seu universitària, compartida, és clar, amb els usos litúrgics i culturals. Aquest és, per tant, un dia molt assenyalat per la Universitat de Lleida, ja que establim un llaç d'un gran valor històric i simbòlic amb el nostre passat. Aquests murs venerables, doncs, evoquen el nostre passat, la tradició, alhora que aquest acte és, en canvi, un homenatge a un investigador, innovador, a l'avantguarda de la ciència mèdica, tradició i innovació, com la nostra mateixa història. En blau també posar de manifest que aquesta investidura és en el marc del 12è International Congress on Molecular Systems Biology. Vull saludar, doncs, tots els congressistes que ens acompanyen i que ens fan l'honor de sumar-se a l'homenatge al doctor Savageau. Sigueu benvinguts a aquesta vella església de Sant Martí, testimoni històric de l'antic Estudi General de Lleida. I would like to greet all the conference attendants who are with us today, honoring us by their presence at this event that has been organized as a tribute to Professor Savageau. Please, be welcome to this old St. Martin's Church, a historical witness of the former General Study of Lleida. La Universitat de Lleida sap que a l'honorar el doctor Savageau, incorporant-lo al nostre claustre de doctors i doctores, ens enriquim, ja que ens beneficiarem del seu prestigi, de la seva saviesa i de la seva humanitat.
Ens podem treure el birret ara?
Tot seguit, la senyora Anna Romero, secretària general de la Universitat de Lleida, ens llegirà l'acte de nomenament del doctor Honoris Causa a la nostra universitat a favor del senyor Savageau.
Benvolgudes senyores, benvolguts senyors, segons acord número 82/2010 del Consell de Govern de la Universitat de Lleida, reunit el proppassat 21 d'abril de 2010, s'aprova nomenar doctor honoris causa al senyor Savageau en reconeixement de la seva brillant trajectòria acadèmica i en especial pels seus estudis pioners en biologia de sistemes.
Prego, doncs, el professor Albert Sorribas, padrí del doctorand, que faci entrar el senyor Savageau. doctor Albert Sorribas per tal que ens faci l'elogi dels mèrits del doctor senyor Michael Savageau.
Magnífic rector, digníssimes autoritats i claustrals, dear colleagues, senyors, senyores, it is for me an honor to address you with the laudatio for the work of Professor Michael Savageau as a candidate to the honorary degree of Doctor Honoris Causa by our university. The Department of Basic Medical Sciences is grateful to the members of the Consell de Govern of the University of Lleida for recognizing his merits and for accepting the proposal for this degree. I will start by introducing the scientific background and the major scientific contributions of Professor Savageau, and then go to a personal appraisal of his impact in the scientific community. Professor Savageau was born some years ago in Fargo, North Dakota. After studying engineering and physiology at the University of Minneapolis and the University of Iowa, he obtained his PhD in cell physiology and systems engineering at Stanford University in 1967. His research interest, right from the beginning, focused in problems related to the integrated behavior of biological systems, mainly gene regulatory networks and metabolic pathways. At this time, I must remember, almost no computer facilities were available to the scientific community, which forced the search for appropriate tools and methods to address systemic complexity in biology at the molecular level. In this context, one of the first questions Professor Savageau addressed was how to represent the different processes within a cell using mathematical models. This is a basic step that still drives the research efforts of many groups, including our own group here at the University of Lleida. The right choice of a mathematical representation allows and at the same time constrains ulterior analysis. An incorrect choice can prevent obtaining any new insight about the system, and an appropriate choice facilitates the understanding of fundamental questions. Starting with methods related to engineering analysis and functions approximation theory, he proposed the power law formulas as a mathematical resort to obtain useful models for biological networks. These models, being relatively simple, capture the essential properties of the constitutive processes of cell biology. This was as early as 1969, right after he obtained his PhD. The power law formulas, as I shall discuss briefly in a moment, was a fruitful idea that opened many new possibilities for the analysis of biological networks. Its use, starting in the 70s, allowed Savageau and others to postulate design principles in molecular biology. Such principles provide objective reasons for why there are, for instance, different modes of regulation for a gene circuit and predict which type of regulatory structure is to be expected in a given situation. Within the domain of gene regulation, meticulous and extensive analysis of the designs of gene circuitry ultimately led to the creation of the demand theory, a theory that explains and has correctly predicted regulatory patterns for gene circuits whose regulation was unknown. Design principles for metabolic pathways have not yet yielded a comparable comprehensive theory, but numerous valuable insights have been gained concerning the hardwiring of representative, simply structured biochemical systems. While working on this class of problems, he also developed a whole set of analytical tools that are applicable to relate the system's behavior to the properties of the underlying processes. The different methods are globally known as biochemical systems theory and can be considered the first serious attempt to devise a new field of research that should bring together experiments and theory to better understand the evolution of biological systems and their adaptive responses. At this point, I shall remember that no analytical methods, experimental methods were, for large-scale analysis of living beings were available at the molecular level. Such analysis was done on a gene-by-gene, protein by protein succession of individual experiments involving enzyme isolation and in vitro mechanistic assays, nothing to do with the modern methods. Also, and I'm talking about the 70s, the role of mathematics in biochemistry was not widely accepted. Savageau's work stressed the already classical idea that the system is more than the sum of the parts, and that the appropriate way to approach such problems was through mathematical methods. Many of the ideas that Professor Savageau introduced went unnoticed by many people because of different reasons. Lack of appropriate data to apply them to the system of interest, lack of computational tools that would facilitate such application, and the dominant vision of the field that was reductionist was thought to be the only way to understand cell biology. While he was working in different analysis of gene circuits and their organizational principles, Professor Savageau continued the methodological developments on the power law formulas as a modeling tool for biological systems. He demonstrated, together with Professor Eberhard Boyd, that nonlinear models can be recast as power law models. This provides a canonical mathematical representation that we can use to tackle different questions. For instance, highly efficient computational algorithms were developed for system models, which are one of the two possible mathematical variants for representing a system using the power law formulas. By focusing in his regular structure, this has a lot of advantages. I still remember my surprise when he showed me the program Essence running in a very rudimentary PC and simulating the dynamic behavior of a quite complex model. This was in 1986 when I moved to the University of Michigan for a postdoctoral stay. To give you an idea of the importance of Essence and as a computational tool and how much ahead of his time Professor Savageau was, I remind you that at that time, believe or not, we were not yet able to connect two computers in a network in order to share a printer. I'm not sure if Professor Savageau remembers this, but we spent almost a week working in his laboratory on this problem of connecting two computers to a printer with an expert from Apple company and without succeeding, so we were not able to do that. Power law models have provided a very fruitful way of representing cellular networks, and many of the colleagues here present and attending this meeting have contributed one way or another to develop new methods and computational solutions to biological problems. These include optimization, computer simulation, parameter estimation, biotechnological applications, etc. The implications of Professor Savageau's work undergo a sudden change with the development of what is now known as systems biology. The success of the Human Genome Project, the development of new high-throughput techniques for gene expression and the sequencing of genomes bring forth the necessity of facing cell complexity in a new way. The rediscovery of the idea of system as a central to biology stressed the necessity of computational and mathematical methods. Bioinformatics contributed to put some order in the big bang of new data that suddenly appeared, but mathematical models were required to integrate them and develop new knowledge. At this point, the early ideas of Professor Savageau appear as premonitory of the new paradigm. Many of us have witnessed the spectacular change in biology that has occurred in the last few years. Today, mathematical models and computational methods are common in many research papers, and they appear in almost any high-impact journal. The search for design principles in biological networks is now one of the hottest topics in biology. Although some of us were expecting this development, the rate at which this change in paradigm is surging now through biology still surprises us. And yet, Michael Savageau is right there with new ideas and proposals to keep us busy. On one hand, he has been working side by side with experimental groups to develop artificially engineered cells with modified gene circuits that help demonstrating some of his all-time ideas. On the other, he keeps pushing the theory further with the proposal of design spaces as a way of understanding the operation of cellular networks. The presence of many colleagues coming from all over the world to attend this ceremony and the meeting we are celebrating here at the University of Lleida is a proof of the success of his work and the many fruitful ideas that he has generated. Many of us have made a whole scientific career by developing such methods, applications and models based on Professor Savageau's work, and we all have benefited from his vision, intellectual rigor and friendship. Nowadays, scientific activity has greatly changed. The pressure for publication, the need for quick results, the lack of funds, etc. constrain one way or another our scientific activity. Because of these pressures and the sudden interest in systems biology, we have witnessed an astonishing increase of new proposals in the field of modeling and analysis for complex systems. As a result, I must say that we have experienced a certain degree of confusion about what is new and useful in this field. Within this confused time, Professor Savageau has managed to maintain his activity focuses on quality, intellectual rigor, independence and creativity. I would like to highlight independence and intellectual rigor as his principal qualities. Because of this, he has always stressed the necessity of developing good scientific results that will be recognized by themselves, whatever the circumstances. Although such recognition is taking more time in some cases than in others, he still holds to those principles which he had right from the beginning. Professor Savageau has been an active member of the universities where he has worked, mainly the University of Michigan at Ann Arbor, at the University of California Davis. He has been chair of the Department of Microbiology and Immunology at the University of Michigan Medical School and the Department of Biomedical Engineering at the University of California Davis. He was the director of the bioinformatics program in Michigan and member of different advisory boards in other universities. He is or has been member of the editorial board of the most relevant journals in the field of mathematical biology, including 10 years as a chief editor of mathematical biosciences. The list of honors and awards include being a fellow of the American Association of the Advancement of Science, Nicholas Rasevsky Distinguished University Professor by University of Michigan, the membership of the National Academy of Science, the Moore Distinguished Scholar for the California Institute of Technology, the Stanislaw Ulam Distinguished Scholar Award, Center for Nonlinear Studies and Los Alamos National Laboratory, and many others. From the work perspective, the work of Professor Savageau has contributed to understand the emergence of systems properties from the interaction of their constitutive elements. This is a fundamental question for understanding evolution and molecular circuits. In that sense, Savageau's work has provided tools and perspective for dealing with evolutive questions in this field. I would like to indicate that these methods allow for solving these questions in a way that cannot be addressed experimentally. In that sense, his work is fundamental as a contribution of what can be achieved with mathematical models. More than just reproduce a given system, but focusing on class of systems, we are now able of understanding complex properties and the emergence of design. This may seem simple now that many groups have entered the race for solving these kinds of questions, but you need to be a clever one to recognize this necessity when almost no one is still addressing them. And Michael Savageau is one of those clever men. Així doncs, considerats i exposats tots aquests fets, magnífic senyor rector, digníssimes autoritats i membres del claustre, sol·licito amb tota la consideració i encaridament prego, d'acord amb la resolució aprovada en el seu dia pel Consell de Departament de Ciències Mèdiques Bàsiques i aprovada pel Consell de Govern, que s'atorgui al professor Michael Savageau el grau de doctor honoris causa per la Universitat de Lleida.
Demano ara a tots els assistents que es posin dempeus per tal d'iniciar el solemne acte d'investidura de doctor honoris causa. Pel claustre de la Universitat de Lleida i com a homenatge als vostres mèrits rellevants, heu estat nomenat doctor honoris causa d'aquesta universitat. Per l'autoritat que m'ha estat donada, us lliuro l'esmentat títol i us imposo com a símbol el birret lorejat, distintiu venerat del nostre més alt magisteri. Porteu-lo per coronar els vostres estudis i mereixements. Rebeu l'anell, ring, que els antics lliuraven en aquesta vella cerimònia com a emblema del privilegi que s'atorgava de signar i segellar dictàmens, consultes i censures que pertorquessin la vostra ciència i professió. I també aquests guants blancs, símbol de la puresa que ha de conservar a les vostres mans i que de la mateixa manera que l'anell són també signe de la vostra dignitat. Incorporat ja al nostre claustre, rebeu ara, doctor Savageau, en nom de tots els claustrals, una abraçada de fraternitat dels qui s'honoren i es congratulen de ser els vostres germans i companys. Bé, prego ara el professor doctor Savageau que pronunciï el seu discurs d'acceptació de formar part de la nostra universitat. Dr. Savageau, please, could you pronounce your speech of acceptance of being part of our university?
Thank you, Director. The title of my address is Challenges in the Development of Molecular Systems Biology. Before I begin, I would like to make a few observations concerning our universities. There are commonalities between my university and yours that suggest that we could be sister institutions. There are also intellectual linkages between our universities in my particular field, which is molecular systems biology, the subject of the conference that's being held here in Lleida this week. I will allude to the importance of these linkages in the following personal account that focuses on three fundamental challenges in the development of molecular systems biology. But first, let me make a few observations about our commonalities. And I quote from one of your publications. The city of Lleida, with 120,000 inhabitants, enjoys a privileged strategic position. It is only 2 hours' drive from the ski runs in the Pyrenees and an hour to the beaches of the Mediterranean. Lleida is located in the center of a rich agricultural region on the banks of the recerca. Now, if I were to loosely paraphrase from that publication, I would say the city of Davis, with 70,000 inhabitants, enjoys a privileged strategic position. It's only 1.5 hours drive to the ski runs in the Sierras and 2 hours to the beaches of the Pacific. Davis is located in the central in a rich agricultural region near the banks of the river Sacramento. Our universities also have commonalities from your website. Again, in 1968, university studies in Lleida were effectively reestablished and consolidated as extensions to various universities in Barcelona. Law, agricultural engineering, arts and philosophy, medicine were introduced near the mid-70s. In 1991, the Catalan Parliament passed an act for the creation of the University of Lleida. Today, it is recognized for its growth and prestige, and it offers a greatly increased number of degrees. Again, a rough paraphrase. In 1908, the university studies in Davis were effectively established and consolidated as extensions to the University of California in Berkeley. Engineering, law, medicine were introduced in the mid-60s. In 1959, the California Regents designated UC Davis as a full-spectrum university. Today, it's the fastest growing of the UC campuses, and it leads the nation in the number of PhDs awarded in the biological sciences. There are also significant differences. The University of Lleida, created in 1300 with links to this beautiful church, recently celebrated its 700-year history. The University of California Davis recently celebrated its 100-year history. So as you can see, we could be considered your younger sibling with only 600 years difference in age. So I'd like to speak about three fundamental challenges in the development of molecular systems biology. And I think of these as representation, comparison, and design. There are undoubtedly many challenges in any field that deals with complex systems, whether they be physical, chemical, biological, or sociological. In addressing the development of molecular systems biology, I will select just three fundamental challenges from amongst those that my colleagues and I have confronted. There have been numerous investigators whose work we have built upon, and there are numerous investigators who have built upon our work and extended it in significant ways as well. The numbers preclude my balanced acknowledgement in this short account, and for this I must apologize in advance. In any event, I trust that there will be significant context that would allow you to search for the relevant references and citations. So the first of these challenges was representation. As early as the mid-1900s, the challenge of representing complex biological systems was well recognized. It was clear that it had to involve mathematics. However, the existing approaches were largely unsuccessful. First, there were many attempts to use well-established linear mathematics, but this proved to be of limited value, since most, if not all, of the interesting properties of biological systems arise from their nonlinearities. Indeed, it has been said that memory, a nonlinear phenomenon, is the essence of human identity. A second approach was based on the principles of mass action adopted from physical chemistry. This too proved of limited value when confronted with the phenomenon of adaptation that proved to involve newly discovered mechanisms of gene control and allostery, not to mention the intractability of the nonlinearities and the issue of parameter estimation in large systems. Yet a third approach attempted to incorporate the nonlinearities associated with these newly recognized mechanisms and build on an analogy to concepts like temperature in the statistical mechanics of physics. However, this approach also proved to be relatively fruitless. This was the state of affairs when I entered the field in the mid-60s, and of course I was influenced by all of these approaches. However, it eventually became clear to me that the existing approaches were not meeting the fundamental, often conflicting requirements for an effective representation of biological systems. On the one hand, the mathematics had to be tractable if it were ever to be really useful in the analysis of complex biological systems. On the other hand, it had to faithfully reflect the fundamental nonlinear character of biological phenomena. After many unsuccessful attempts at representation, I discovered the analogy between the rational functions of biochemical kinetics and the transfer functions of electrical circuits, which ultimately proved fruitful. To give you some background, the explosion of growth in molecular biology that occurred in the latter half of the 20th century, which is often referred to as the biological revolution, the focus of this reductionist period was on the discovery and characterization of the basic components of organisms. Interest of the integrated system was largely on the periphery. Not surprisingly, biochemical kinetics during this period was focused on the rate laws of isolated enzymes and steady states. And there were no generic tools for extending these approaches to large systems of reactions relevant for biology. By contrast, the theory of electronic circuits was already well developed by the mid-50s. Intellectual giants such as H.K. Boddy had developed rigorous tools for the analysis, synthesis, and control of large complex circuits. One of his more practical discoveries was the importance of decomposing systems into modules and treating their dynamics in the frequency domain using log-log graphs known today as Boddy plots. By building on this analogy, I discovered that biochemical rate laws could be represented in a logarithmic coordinate system and approximated by the leading terms of their Taylor series to produce a local nonlinear representation. When the representation in logarithmic coordinates is transformed back into Cartesian coordinates, the result is a set of equations involving products of power law functions. This representation, now referred to as the power law formalism, allows one to quantitatively relate the behavior of an intact biological system to the properties of its underlying molecular determinants. It was recognized from the beginning that this formalism could be considered a canonical nonlinear representation from three different perspectives. From the fundamental perspective, it provides a generalization of mass action, which traditional kinetics is mass action kinetics is a special case. From the local perspective, it provides a general representation in logarithmic space that is guaranteed by Taylor's theorem to be accurate within a well-defined neighborhood about a normal operating state. From the piecewise power law perspective, it provides a global representation constructed from a set of local descriptions that can be made as accurate as desired, again according to Taylor's theory. Subsequently, my colleagues and I discovered that the power law formalism could be considered a canonical nonlinear representation from a fourth perspective. From the recast perspective, it provides an exact global representation for an enormous scope of nonlinear equations. Thus, the power law formalism provides a nonlinear representation that is sufficiently general to describe biochemical models composed of rate laws having essentially any form of biological interest. Later, in discussing the issue of biological design, I will have occasion to mention how one makes use of all four of these perspectives in describing these systems. The appropriateness of any representation is ultimately determined by its ability to make specific predictions that are confirmed by experiment. There is now a wealth of examples by which this formalism has been used to predict the function, design, and evolution of biological systems, and for which there is confirmatory experimental evidence. Many colleagues participating in the conference this week have enormously expanded this activity with research programs on biological systems at various scales, from molecular and cellular to organismal and ecological. Indeed, the general character of these methods has led to applications in areas beyond biology as well. When this work first came to the attention of others, there were some who criticized our methods for lack of applicability and inaccuracy compared to alternative methods. One of the first to recognize the fallacy of these claims was Albert Sorribas, professor and chair of biostatistics here at the University of Lleida, and soon to be vice rector for research and organizer of the International Conference on Molecular Systems Biology. Professor Sorribas, my first intellectual link to the University of Lleida, addressed this issue directly by making a detailed comparison of the alternative methods in the context of a metabolic pathway involving protein-protein interactions, an issue of some metabolic interest at the time that has since become a major focus of genomic systems biology. His results demonstrated that our methods were not only applicable to this phenomenon, but they were capable of representing it more accurately than the alternative methods. Professor Sorribas has since been an active contributor to this field, exploiting the generality of the methods he helped develop and extending them into entirely new areas such as computational statistics and genomics. So the second major challenge was comparison. And comparison plays a central role in scientific research. Hypotheses making alternative predictions are tested in experiments. The hypothesis that provides the better agreement with reality is refined and subjected to further tests and comparisons. This is the textbook description of the scientific method. In practice, things are never so simple, particularly in dealing with complex biological systems. There is a story told by Paul Tillich, a prominent theologian in the 1960s, in which his son asked him a question that stimulated him to his most productive work. The question was, why is there something and not nothing? A number of philosophers and cosmologists are also interested in this basic question. A less philosophical but equally profound question of interest to biologists is, why is there something and not something else? Why is there in nature only certain molecular components, certain biochemical systems, certain organisms that have been selected rather than others? In the mid-20th century, this was a particularly difficult problem for evolutionary biologists. At that time, one could not really do evolutionary experiments, and the notion of making a well-controlled comparison of alternatives did not exist. As a result, many explanations in evolutionary biology involve long and often eloquent arguments that were essentially circular. When stripped to their essentials, they often went something like the following. Why did X evolve? Because it had a selective advantage. And how do you know it had a selective advantage? Because it evolved. Now, with such arguments, one could produce superficially satisfying narratives for almost anything. Eventually, these were rightly criticized as, quote, just so stories, unquote, in reference to the delightful children's tales of Rudyard Kipling. This changed when evolutionary biologists realized the potential of bacteria as a model system for the experimental study of evolution, and the intellectual gulf between the molecular and the evolutionary biology communities began to narrow. However, answers to the profound questions remain elusive. This intellectual milieu provided the stimulus for me to propose basic attributes that should be possessed by any theory of alternative designs for biological systems. Such a theory should provide three fundamental capabilities. First, it should provide an appropriate language or formalism or context in which you can describe the alternatives. Since many of the alternatives no longer exist, generic methods of accurately representing their behavior are required so that comparisons can be made in principle, at least, just as if the alternatives did exist. Second, it should provide methods for relating system behavior to changes in elements of the design. These methods must be tractable, systematic procedures so that an arbitrary number of possibilities can, in principle, be examined. Third, it should provide methods for critically comparing the behavior of the alternatives according to objective criteria that can be quantified. Although a general theory that would possess all these attributes and provide understanding for alternative biological systems has yet to be formulated, my colleagues and I have developed the rudiments of such a theory and applied it successfully in a number of instances. The first of the above capabilities, the generic representation, is provided by the power law formalism, as noted earlier. The second capability, relating system behavior to changes in elements of the design, also has been developed within the power law formalism, building on well-established theory from engineering systems. The third capability, critically comparing the behavioral alternatives according to objective criteria that can be quantified, is no trivial matter in complex systems. To address this last capability, I proposed a method called mathematically controlled comparison that combines aspects from several existing approaches. Its characteristic features can be summarized in very abbreviated form as follows. The two designs being compared are restricted to having differences in a single specific process that remains embedded within its natural milieu. This is equivalent to a single mutational difference in an otherwise isogenic background. This is called internal equivalence, and it provides a means of nullifying or diminishing the influence of the background, which in complex systems is largely unknown. Second, the two systems are required to be nearly equivalent as possible in their interactions with the outside environment, from a perspective external to the system, which is called external equivalence. The one altered process will in general have a different set of values for all its parameters. This introduces extra degrees of freedom that, if not constrained in some way, allow you to make any result possible from the predictions, from the comparisons. The conditions imposed by external equivalence fix the values of parameters for the altered process in such a way that arbitrary differences in the behavior are largely eliminated. Functional differences that remain between the two systems with maximum internal and external equivalence represent inherent functional differences for the designs in question. The method of mathematically controlled comparison has been used for some time to determine which of two alternative regulatory designs is better according to specific quantitative criteria. In some cases, the results obtained are general and qualitatively clear-cut. One design is always better than another, independent of the parameter values. In contrast, an ambiguous result is obtained when either of the alternatives can be better depending on the specific value of the parameters. This issue was addressed by Rouly Alves associate professor in biostatistics here at the University of Lleida, and another organizer of the international conference this week. Professor Savageau, my second intellectual link to the University of Lleida, developed a numerical approach to this problem by combining the method of mathematically controlled comparison with novel statistical techniques to yield numerical results that are general in a statistical sense. This approach retains some of the generality that made mathematically controlled comparison so attractive, and at the same time provides quantitative results that are lacking in the symbolic approach. For example, the symbolic approach may well prove that one design is always better than another, but the numerical approach might show that the differences are insignificant or minuscule. For those cases in which the symbolic approach shows that one design is superior under one set of conditions and inferior under a different set of conditions, the numerical approach might resolve the issue by demonstrating that only the first set of conditions leads to a statistically significant difference between the systems. Professor Savageau has gone on to address alternative designs for signal transduction cascades, as well as other classes of mechanisms using structural genomic approaches. Which brings me to the third challenge that we have faced in the development of molecular systems biology, and that is design. For a long time, the issue of design in biology was not legitimate. In some quarters, it is still considered a taboo subject. This is a legacy of its misuse in arguments against evolution and in the just so stories of early evolutionary biologists. However, the term design has a rich and well-established meaning, and when used in the context of rigorous analysis and objective performance criteria, provides a deep understanding of the function and evolution of biological systems. This is now more widely accepted, as is evident in the books that are being published on the subject of biological design principles, the establishment of new journals with this focus, and conferences such as the current one being devoted to the subject here in Lleida. Any discussion of design raises the question, are there design principles or rules that govern the patterns observed among biological systems? The answer depends on who you talk to. There are some biologists who would answer, of course there are rules, and it's the business of science to discover them. This is the structuralist view that is a long tradition embedded in positivist philosophy. Collection of empirical data, induction of rules, synthesis of general laws. Rahe, Kepler, Newton provide the paradigm. On the other hand, there are some biologists who would answer that question as follows. No, there are no rules. Anything is possible. There is only what exists to be discovered in history. This historical view is part of the Darwinian legacy, and according to some, it has become the dominant view in modern biology. In the mid-'80s, Gary Webster and Brian Goodwin provided an extensive account of these contrasting philosophies in the context of developmental biology. Anyone interested in the subject would be well advised to read their article. Differences may be seen in the detailed molecular mechanisms by which a given type of system is realized, and one can always assume that the differences are the result of historical accidents or contingencies. But such explanations have no predictive power and tend to stifle the search for alternative hypotheses. It generally tends to be more productive if one starts with a working hypothesis that there are rules. One may well end up attributing differences to historical accident, but in my opinion it's a mistake to start there. Modern systems in synthetic biology face two major challenges involving issues of design. How can one elucidate the relationship between the information encoded in the genome and the context-dependent expression of that information as manifested in the phenotypic repertoire of an organism? The first is the fundamental unsolved problem of relating the digital representation of the genotype to the analog representation of the parameters for the molecular components of the system. For example, knowing the DNA sequence of an enzyme does not allow one to determine its kinetic parameters. The second is the fundamental unsolved problem of relating the parameters of the components and the environment to the phenotype of the global system. For example, knowing the parameters does not tell one how many qualitatively distinct phenotypes are in the organism's repertoire, nor does it reveal their relative fitness. These also are challenges for clinicians trying to develop therapeutic strategies for treating pathology. or biomedical engineers attempting to redirect normal cellular functions for biotechnological purposes. Although astonishing advances in addressing the first of these fundamental challenges have been made, and many more are sure to come, there has been, by comparison, a conspicuous absence of advances related to the second. If we are to relate genotype to phenotype, we must start with a clear idea of what we mean by the phenotype. Although we have a good idea of what we mean by the genotype, that's now the complete DNA sequence for an entire organism, many organisms, including humans, it's less clear what we mean by phenotype. At the level of the organism, we have a few examples that we all know of, things such as hair color of cats, size and shapes of flowers, height and weight of livestock, not to mention disease states in humans. The difficulty in relating these two levels of biological organization and function is hard to overestimate. Moreover, between the levels of genotype and phenotype of the organism, there are many intervening levels that form a rich hierarchy of cell and molecular subsystems. Although there are some intuitive notions of what is meant by phenotype at the level of the organism, it is far from clear what the term phenotype means at the level of these intervening systems and what the phenotypic repertoire of any given system might be. To address this challenge, my colleagues and I have recently introduced this concept of a system design space in which qualitatively distinct phenotypes of a model can be identified and counted, their fitness analyzed and compared, and their tolerance to change measured. Application of this theory to a number of simple, well-characterized systems, such as the lactose operon and bacteriophage lambda, have provided some proof of principle. Each of the design spaces constructed to date is unique, representing a sort of fingerprint of the system. The construction of a system design space is based on the power law formalism and makes use of all four of the perspectives that I mentioned earlier: the fundamental, recast, local, and piecewise power law. The result of this construction, which has been automated, is a partitioning of the design space into regions that exhibit qualitatively distinct behavior. Thus, the regions provide an unambiguous definition of molecular phenotypes for the original system. The parameters of the original system define landmarks in this design space, and the particular constellation of parameters that define these landmarks often reveal important system design principles that are not at all obvious and would be difficult to discover. For example, the system design space that has been constructed for this virus, phage lambda, it's a bacterial virus with a biphasic lifestyle that has been has revealed its system design principles involving this. The virus can infect a cell and rapidly replicate, eventually killing its host and releasing virus particles to go on and infect other cells. This is the lytic growth phase that the virus can exhibit. Alternatively, on entering the cell, it can insert its DNA into the chromosome of the host and become quiescent and simply reproduce along with the unharmed host cell. This is the lysogenic mode of growth. The system design space for lambda reveals the following design principles. There is a band in this space in which a constellation of the parameters must fall in order to maintain the long-term survival of this biphasic lifestyle. If the constellation of parameter values lies above the band, then the phage would be locked into the lytic style of growth, like other viruses, some other viruses, like T4. On the other hand, if it falls below this band, then the virus would be locked into the host chromosome and could no longer become lytic, and therefore would die when its host dies. Similar design principles have been found for other systems as well. In conclusion, I would say that although my colleagues and I have contributed to other aspects of molecular systems biology, I consider the three that I have been emphasizing here to be among the most significant. This undoubtedly reflects my own interests, talents, limitations, as would any such account. It also reflects a set of scientific values and experiences that have formed my perspective. When I began my career, there were few individuals with the interdisciplinary training that I had received in systems engineering and cell biology at a premier university. Thus, I brought a nearly unique perspective to the field that has since become molecular systems biology. Today, the investigation of design principles in molecular systems is becoming increasingly important for the understanding of complex biological systems. And although there are a number of successes that have made the effort legitimate, this is a rich and relatively unexplored domain. The rise of a new generation of investigators addressing these issues with a focus on the interface between biology and the other quantitative sciences bodes well for the future of this endeavor. Finally, it is a great honor to receive this doctorate and a very humbling experience to be included in the company of other luminaries that have received this honor from the University of Lleida. It's also a particularly pleasant occasion because so many are present here with whom I've had the privilege of collaborating over the years. I've already mentioned Albert Sorribas and Rui Alves because of the special connection to the University of Lleida. I also have had the good fortune of working with many other talented colleagues, including Eberhard Voigt, Masahiro Okamoto, Fumihide Shiraishi, Armindo Salvador, Michael Wall, Oleg Igoshin, Dean Tola, Pedro Coelho, Rick Fasani, and Jason Lomnitz, who are here, and many others from around the world who could not be here. I'm indebted to all of them for intellectual support and for the sharing of ideas. And in the interest of full disclosure, I should also acknowledge that my wife Anne, who is a professor of design, she claims to have a major influence on my interest in the subject. So I thank the University of Lleida for this wonderful event and for the many colleagues and friends for coming to share their passion for furthering the development of molecular systems biology. And thank you all.
Diré primer unes paraules en anglès per explicar als nostres visitants la Universitat de Lleida i el lloc en el que estem. University of Lleida is a young institution, but with a very deep historical roots. In 13th century, King John II created what was called the Estudi General de Lleida, the first university center of the Crown of Aragon, and over 150 years, the only institution of this kind in the whole kingdom, so that for centuries our town was the meeting point which forget for the unity of the Catalan language and culture. Our University of General Study was closed, like the rest of institutions of a Catalan country, including Barcelona University, by the Spanish King Philip V the Bourbon. From that glorious past, to which the University of Lleida feels here, now only stands this old Romanesque church of St. Martin, a site where the most solemn university acts were celebrated. In this same church, the rectors and presidents of our university were nominated since its foundation until the 18th century. Our Estudi General of Lleida stood out in medical studies. Let me remind you of that at this event. In the West, at that time, the best medicine was Arabic. And Lleida had been a Muslim city until the mid-12th century. Arabic medicine was often known by means of the translations that were made by the Jewish physicians, and which James II, founder of the study, personally got translated to the vernacular language. Some of those teachers and scholars were very important figures at that time, such as James of Agramunt, who was a leader in the fight against the bubonic plague, the most dreadful scourge at that time. The prestige achieved by the medical studies of Lleida allowed this university to obtain, in 1391, following the example of Montpellier, the privilege of King John I authorizing the delivery every 3 years of the body of the person who had been sentenced to death, so to students could learn anatomy. Certainly a notable advance in Europe at that time. Once, however, the incisions and mutilations were performed, they gave ecclesiastic burial of the unfortunate victim. These venerable walls, therefore, evoke our past, our tradition, while this act is, in contrast, a tribute to innovative research at this cutting edge of medical science, tradition, and innovation, like our own history. Our university was restored as independent in 1991 after having depended of the University of Barcelona since the 19th century. Our buildings are new, and we have many modern facilities improved in recent years. We have gained prestige, and our researchers and professors have made it possible for the University of Lleida to achieve the first place in the Spanish universities in some research rankings in life science last year, 2010. We are improving our international relations year by year and have agreements with hundreds of other universities all around the world, with hundreds of foreign students coming to study here. For us, then, is it an honor and a great pleasure to include you, Professor Savageau, in our cloister of doctors. We heard the excellent Laudatio and your excellent conference. Professor Sorribas is one of our great professors and researchers. And next week, he will become Vice President. He has demonstrated his knowledge to us, and does not surprise me, as I know him quite well. I thank his proposal. I thank you, your proposal, Professor Savageau, as honorary doctor. I shall not repeat your merits, Professor Savageau. I will just highlight your quality, intellectual rigor, independence and creativity, your independence in developing good scientific results that will be acknowledged even if it takes some years later. In Catalonia, we say, a job well done is never a hindrance and has no borders. Careless work has no future. La feina ben feta no té destorb ni fronteres. La feina mal feta no té futur. The subjects of your research are very important for human health, for improving our quality of life. Good research is interdisciplinary today. It requires us to be mathematicians, physicians, chemists, bioinformatics, biologists, physicians, surgeons, dietitians, philosophers, etc. The current impact of new technologies is great in all scientific research. They are absolutely necessary. In the near future, we shall be able to practice medicine adapted to the specific needs of each patient, giving them exact doses that can never be metabolized, that can be better metabolized and help their rapid recovery, thanks in great measure, as Professor Sorribas said before, to mathematical modeling, your area of specialization. For the advance of medicine and basic research, it is essential to know about cellular cycles, cellular stress, molecular functioning, genetic expression, for instance, which look far away from the operating theatre. But thanks to all that research, we surgeons can operate patients in better conditions and allow for better and faster post-operative recovery. We must continue learning from the way science is organized in the United States. I confirm that during my stay in the University of Minnesota, one of your universities you have to work, or during my visit to Davis University, part of the public university system in California. Another important aspect that I want to highlight is that in a lot of research, and especially in Professor Savageau's research, there is an important scientific philosophical component added to the ethical and bioethical ones. Thomas Kant, in his book, The Structure of the Scientific Revolutions, studied these aspects of the behavior of the scientific community. A scientist is able to look at nature and the problem to study with new eyes, new approaches to the well-established knowledge of the scientific society. Savageau proposed new theories, such as the man theory, that allowed him to move forward, to open new doors to science, to formulate new paradigms, which, after not being accepted for a long time, the scientific community has ended up surrendering to. That is a good example. Thanks, Professor Savageau, for dedicating your full life to produce good science. And now I will continue in Catalan, our first language. La ciència fa grans salts quan un investigador és capaç de mirar amb ulls nous, els que permet descobrir coses noves a la natura cada dia. Noves teories, com la de la demanda, com ha demostrat el professor Savageau, li ha permès anar molt lluny, obrir noves portes a la ciència, crear nous paradigmes que no han estat acceptats immediatament, però que davant dels quals la comunitat científica ha acabat rendint-se a les seves teories i de recerca. Tot un exemple. Tal com ha expressat el professor Sorribas, gràcies al seu treball de models matemàtics, el professor Savageau avança ràpidament vers una medicina del futur, que serà una medicina a la carta. Podrem saber la dosi més exacta per a cada malalt, el que més li convé menjar, els riscos que té per a la seva salut, etc. Ja no servirà allò d'un comprimit cada 8 hores, sinó la dosi específica que metabolitzarà millor i el portarà a la curació el més ràpidament possible i amb menys efectes secundaris. També ajudarà a fer millor la cirurgia personalitzada i tot això gràcies als models matemàtics que estan tan lluny de les sales d'hospitalització o de les sales d'operacions. Personalment, he fet una estada a la Universitat de Minneapolis, una de les que ell ha treballat, i he comprovat com és una gran universitat. I he après molta cirurgia i gestió. També he visitat la Universitat de Califòrnia, a Davis, la seva universitat a la qual treballa. Ell ens ha exposat les semblances entre la Davis University i la Universitat de Lleida. Estem aprenent molt dels Estats Units i encara ens queda molt per aprendre. Veiem que en una ciutat petita inverteixen per convertir la seva universitat en referent mundial en una especialitat, però excel·lent en moltes altres disciplines. No se'ls acut concentrar en grans capitals tota la ciència i la indústria. Ans al contrari, porten la ciència especialitzada on hi ha l'interès i les possibilitats de l'entorn. Ni la capital de Califòrnia, Sacramento, és la més habitada, sinó que és més aviat petita. Ni porten ni concentren la ciència a San Francisco, per exemple, la ciutat més gran de la Califòrnia del Nord. Ni el sistema públic que es diu Universitat de Califòrnia es menja les universitats que li formen part, que lluiten per si soles i prestigien el conjunt, com Berkeley o Davis, estiguin en una capital o estiguin en un poble. Bé, per tant, per acord per unanimitat del Consell de Govern de la Universitat de Lleida i a proposta del Departament de Ciències Mèdiques Bàsiques m'ha plagut atorgar aquest títol de doctor honoris causa i incloure en el claustre de professors i professores el professor Savageau, a més de fer-lo a aquesta església de Sant Martí recuperada pels actes acadèmics al segle XXI, com es feia des del segle XIV, en el que és el meu darrer acte com a rector de la Universitat de Lleida. I abans d'acabar vull agrair al cor de l'Orfeó Lleidatà, sota la direcció de Maria Altadill, la seva participació en aquest acte i felicitar-lo per les seves magnífiques interpretacions musicals. Moltes gràcies. Prego ara a tots els assistents que ens posem dempeus per participar en el cant del Gaudeamus Igitur.
Ens expliquem això o no expliquem això?
Després, mucho calor. Teniu aquí. Viva